this is Himabindu, Assistant Professor in IARE College. So today in this video, I would like to explain about the linearly bound automata. So what type of languages we are going to construct the linearly bound automata, and what type of grammars we are going to use this construction of linearly bound automata, we will see. So what is meant by context sensitive grammar? So coming to the Chomsky hierarchy, every time we are discussing in every video. So first we need to tell about the how many types of grammars we have in the theory of computation. So coming to the Chomsky hierarchy, regular grammar. So regular grammar. So is type 3 grammar. So this is the type 3, and the context free grammar. So this is one subset of, so regular grammars are the subset of context free grammars. So this is a type 2 grammar, and we have context sensitive grammars. So context sensitive grammars, so this is one more type, this is the type 1. And we have one more unrestricted grammar. So unrestricted grammar, we can rate it as a type 1, type 0. So these are the different types of grammars we have in the theory of computation. So in this one, we are going to discuss about the context sensitive grammars. So context sensitive grammars having the production rules and non-terminals and terminals. So generally, we will denote the grammar with the for tuple notation. So what is meant by grammar? So it is having that combinations of V is nothing but non-terminals which are represented with the capital letters, and T is nothing but which are the terminals which are going to be denoted by the small letters, and P is the productions. So productions which are based on the alpha tends to beta. So alpha and beta which are having the values, like it's a combination of V and T. So V union T, we can add both the terminals into the production rules. And S is the starting state. So this is the general notation or general definition of every grammar. So in this one, we are going to discuss about the context sensitive grammar. So this is a subset of unrestricted grammar. So we have 4 types of grammars here. So in this one, we are going to discuss about the type 1 grammar. So what that is nothing but it is a context sensitive grammar. So it is an unrestricted grammar in which all the productions are of the form alpha tends to beta. So we discussed every production rule is in the form of alpha tends to beta. So here are some limitations. Unrestricted grammar it is. So in this one we have some limitations. So in the context free grammar we are having production rule like this. So context free grammar, the production rule is of type. So only single non-terminal which is related with the V union T. So here we are left hand side we have only one non-terminal, and right hand side we have, it's a combination of terminals or non-terminals, or single terminal is also acceptable. So that is the context free grammar. So context free grammar. And here coming to the context sensitive grammar, we are going to give the limitations for the unrestricted to this production rule. So in context free grammar, we have only one value. Left hand side we have only one length of string is there, and here in the right hand side we have the length more than 2 or more. So here this left hand side only a single value is the restriction in the context free grammar. Coming to the context sensitive grammar, we can use both V and T in the left hand side also. That is the difference from the context sensitive grammar. So context sensitive grammars are more powerful than context free grammars. Why? Because this limitation is overcome in the context sensitive grammars. So grammar, because there are some languages that can be described that can be described CSG, but not by the context-free grammar. So obviously, some grammars which are going to be only represented with the context-sensitive grammars, but not with the context-free grammars. That's why we can say that context-sensitive grammars are more powerful than context-free grammars. And here, the context-sensitive grammars are positioned in between the context free and unrestricted grammar. So this we already discussed. So where this the position of context free, context sensitive grammars are in between unrestricted grammar and context free grammars. So this is about the context sensitive grammar. And coming to the definition, we have this, we generally will represent n with the non-terminals, so non-terminals, and epsilon, with this is nothing but a terminals, and p is nothing but it's the production, and s is nothing but it's a start symbol. So these are the n is nothing but a set of non-terminal symbols, and which is denoted by capital letters. Capital letters. And sigma is nothing but it is a terminal symbols which are represented with the small letters. And the S is nothing but it is a start symbol, and P is nothing but a finite set of productions. So all the rules here, all the rules in P are of the form alpha A1, A alpha 1 A, alpha 2, alpha 1, beta, alpha 2. So this is the production rule formation. So here the production rule is like this. So this is the production rule. So generally we have the restrictions in context-free grammar like this. So context-free grammar. So context-free grammar production rules are of this form. So no, alpha tends to beta. So here alpha tends to beta here. Only one value and two. So alpha is equal to only one value. Length of V is equal to 1. And beta tends to the length of V union T is greater than 1. Greater than or equal to 1. So this is the context free grammar. And coming to the context sensitive grammar, the production rules are of the form alpha 1 tends to alpha 1 A, alpha 2 tends to beta 1, sorry, alpha 1 beta alpha 2. So here there is the production rules are like this. The length of context sensitive grammar, the left hand side of every production. So it's a combination of V union T. Sorry, here also V union T. So V union T. We'll write it as a V and T. And here the length is greater than, less than or equal to V union T. So left hand side and right hand side, we need to check for this condition. So left hand side, the length of the production rule from the left hand side is less than or equal to right hand side of the production. So this is the limitations, and we are going to use in the construction of linearly bound automata. And context sensitive language. So the language that can be defined by the context free grammar is called CSL, context sensitive language. The properties of CSL are every time for regular languages or regular grammars, we are having some operations or properties for the in between the two grammars. So here also we have some properties for the context sensitive language. So union operation and intersection and concatenation of two context sensitive language is context sensitive. So whatever the operation, union, intersection and concatenation of two context free grammar, context sensitive grammars. So context sensitive grammars is resulting as a context sensitive grammar only. And here the operation with the intersection of two context sensitive grammars is equal to the context sensitive grammar only. And here the complement of context sensitive language is context sensitive only, and the complement of CSG, and here the concatenation of two grammars. So here is the dot represent, it is a concatenation, also results in the context sensitive grammar only. And here one more operation C context sensitive grammar of one complement is also equal to the context sensitive grammar. So these are all the properties of context sensitive grammars. And here is the example. We have the language length, left hand side and right hand side of every production. So here S tends to ABC, either it is a terminal or it is a combination of both terminals and non-terminals. And here the length is, if you observe the length which is less than or equal to right hand side of every production. So left hand side of every production length is less than or equal to right hand side of every production. So here AB and BA, and here AC is there, here length is 2 and here length is 4. So that is 2 less than or equal to 4. And here also 2 less than or equal to 4. This is also satisfied. And here these are all the language of productions which are having the grammar which are having the productions are all in the form of context sensitive grammar. And what is meant by linearly bound automata? So linearly bound automata is nothing but what we can generate the language context sensitive grammars which are going to be generated by the linearly bound automata. We can accept the linearly bound automata with the context sensitive grammars. And a Turing machine that uses only a tape space occupied by the input is called linearly bound automata. Generally, this LBA is represented as TM, Turing machine plus input space tape. So, if you observe the Turing machine, so we already discussed the Turing machines in the last videos. So, how to denote the Turing machine and what type of requirement is for Turing machine, we already discussed. So, Turing machine, which is having the infinite memory. So, infinite tape length is there in the Turing machine. But coming to the, what we are saying, the linearly bound automata, it's a Turing machine plus, so Turing machine operations, what we are having, it is the controller which is a finite controller which can move either left or right directions or left or right. General Turing machine. So standardized Turing machine we are discussing. So this finite control can move either left or right operations. So that Turing machine along with the input space tape. So here in the Turing machine, we took only infinite memory tape. But in the linearly bound automata, we took input space tape. So that is nothing but here, this is the linearly bound automata. So this is the input tape. We can, instead of this finite, we will write the limited space like it is bounded by the arrow marks like this. So in between whatever we are going to write, that is nothing but input space tape, what we call it as a input tape space. So here this linearly bound automata, we have a Turing machine plus input tape space. And the operations are all equal to the Turing machine. So we can move either left or right directions. So here, additionally, the Turing machine, so instead of B blank symbol, we are going to use this left hand marker and right hand markers. So to bound the input space, to bound the input space, we are going to use this two additional symbols, and that's why it is named as a linearly bound automata. So linearly bound, so it is a bounded in between the two symbols. The input is going to be bounded in between the two symbols in the input tape. So here there are two special symbols that what we are seeing, left hand marker and right hand marker. So here we can write it as a left bound of tape that we can represent here like this, and right bound of tape like this. So this says that we can, by seeing this tape, we can say that it is a linearly bound or infinite memory Turing machine. So Turing machine begins in the configuration like so S. So in between the symbol, so input symbols what we are having. Suppose here S is the start symbol, and here the input what we have, input string what we have taken, that is in between the two markers, that is left hand marker and right hand marker. And initially we'll represent the infinite tape with the Z naught like that. And here the Turing machine cannot replace these two values. So we can't replace these values. So replace in the sense the operation. So here the input what we have taken, we can change, we can replace the input values, but we can't change the boundaries. So boundaries we can't change. So with everything, anything else, not move the tape ahead, left or right direction. So we can't even move a tape space, input space also. So this boundary is not going to be changed. So this is the linearly bound automata limitation. We can't move from left or right. So whatever the input space given in the input tape, what that is going to be used. So whatever the boundaries we have, we are not going to change that values here. So this is about the linearly bound automata. And coming to the definition, so generally for finite automata, we have this is a fine. We'll just generalize the all automatas here. So in finite automata, we have it a finite amount of memory is required here. Finite memory is required. So here that's why for some languages we can't construct a finite automata. That's why we are going to the PDA, push down automata. So PDA requires here in finite automata only a finite amount of memory is required, and coming to the PDA, infinite amount of memory, infinite amount of memory. So here, so coming to the PDA, it requires infinite amount of memory, so that whatever we can't build with the finite automata, we can construct the PDA. And coming to the after PDA, so I'll write it neatly. So finite automata. So which is more powerful than PDA is more powerful than finite automata. Why? Because here a finite amount of memory is required, and here infinite amount of memory is there. So that's why it is a more powerful than finite automata. After that, what we are going to discuss? We are going to discuss about the linearly bound automata. Linearly bound automata. So why? Because here the bounded input space tape we are using. Input space tape. That's why more infinite. Here infinite memory with the stack we are going to use, but this stack which is not suitable for some different languages. So we'll discuss what type of languages that we can't construct with the PDA, construct a PDA, and for the same example how we can build the linearly bound automata we will discuss. So here And linearly bound automata is more powerful. Why? Because for some languages this type of PDA is not going to be accepted. So the kind of languages which are going to be accepted by the linearly bound automata, and these are all which is more powerful than Turing machines. So Turing machines are more powerful than these three. So why? Because it is a infinite tape is used here. Infinite tape we are going to use. So we can insert many values and in the infinite amount of tape. So what are the limitations? We are discussing about linearly bound automata. So what type of languages we are not going to be we are not going to construct a PDA. So here in the previous videos, we discussed about the example a power n and b power n and c power n. So here with this example, which is going to be, which we can construct a PDA, push down automata we can construct. So here n number of A's followed by n number of B's. And whenever the input symbol additionally we have, we are not changing the values in the stack. We are not changing the values of stack, and we are just simply directly going to the finite automata with the input symbol C also. Whenever the language, this kind of language is there, so here we have the n number of A's followed by n number of B's and also n number of C's. So this kind of languages we can't construct a PDA. So how big? Why? Because here n number of A's followed by n number of B's. So here in the n number of A's, when we are reading the A value, we are going to insert the values into the stack. While reading the B value, we are going to pop the B's, so that number of A's are equal to the number of B's is satisfied. And C, while reading the C value, we just we are not doing anything, and we are going to the final state with the initial step of the initial stack symbol. So that like that we can construct a PDA for this kind of language. And coming to the A power n, B power n and C power n. So this kind of language. So here if you read A, we are going to insert the values A into the stack, and while reading B, here we are going to read the pop the values of A's, so that these two conditions are satisfied. And what about this one? So C power n, which is not there. So we need to compromise this. We need to do the equality between these two symbols, so that we can't insert the C value and we can't pop the values, so that's why we can't construct a PDA for the A power n, B power n and C power n. And how we will design this automata, in the sense we can use this language and we can construct the language for linearly bound automata. So how we will see how to construct a linearly bound automata for this kind of languages. So before that, what are the definition of linearly bound automata? So it is having the how many tuples? So here 8 tuples are required here. So what are those 8 tuples? So Q is nothing but it is a finite set of states. So how many transition states are there? We are going to discuss the transition state. And T is nothing but terminal symbol. So whatever the input string values are there, we are going to represent with the T or epsilon. And E for here input alphabet, and T for tape. Sorry, here it is not. So here it is a tape symbol. So here whatever the values we are going to insert into the tape. So what is that in the sense? While reading 0, we need to replace it with X. And while reading 1, we need to replace it with Y. So that kind of whatever we are going to insert the values, those values are represented with the tape alphabet. And E for input alphabet. So input alphabet epsilon symbol, we can represent it as a epsilon also. And Q naught is the initial state, and M, L and M or the left boundary and right boundary, and S is the starting state, and F is the, so S is the transition function, or else we can represent it with the delta, and F is a finite set of final states. So here, for how many states are there, final states are there, those are all represented with the F. So this is the general definition of linearly bound automata. So, what are the results about the linearly bound automata? So, by using this linearly bound automata, we can solve this kind of problems. So, what are the problems in the sense? Halt problem, membership problem, and emptiness problem. So, here halt LBA. So, halt of LB, HALT LBA. So which is M value and W. So M is a linear bound automata and M halts on W. So M halts on W is nothing but the string. So which is going to be decidable, and LBA that stops on input W must stop in at most alpha of W steps. So here, so the halting problem is solved with the linear bound automata. And membership problem. So what are the membership problem is there? So that is also decidable, and it can accept the linear bound automata can accept the W also. And emptiness problem. So for every Turing machine, there is a linear bound automation. So which accepts the set of strings which are valid, halting computation for the Turing machine. So this is about the emptiness of problem. So emptiness problem which is solved by the linear bound automata. And what are the standard examples of linear bound automata? So here, these are the examples. Generally, we can construct the linear bound automata. This kind of languages we can construct linear bound automata. And for this kind of languages, we can't construct a finite automata, or we can't construct a push down automata. So we just only construct the linear bound automata. In this one, so first one is a power n, b power n and c power n, and n factorial, and here a power n. So n is equal to the m power 2. So these are all the different types of languages we can construct the linear bound automata. In this one, most popular example we will discuss. So a power n, b power n and c power n. So how to design the linear bound automata? So generally we have the input step. So input step which is bounded in between. So these are the boundaries. So we'll write it as a left end marker and right end marker, or we will represent with the square braces. So like this. And here a power n, b power n and c power n. First we need to elaborate the language. So n greater than or equal to 1. Suppose if you take a power n is equal to 1. So what is the language string? So a, b, c. And if you take n value is equal to 2. So a power 2, b power 2 and c power 2. So what it indicates? A, b, b and c, c. And also we have a power 3, b power 3 and c power 3 and so on. So here in this one we will take this example B and triple B and triple C and so on. So in this one we will take this a power 3, b power 3 and c power 3. So this kind of, we will take one string and we will design the linear bound automata. So A, and B, B, B and C, C and C. So these are the input string. So for this one, first what we are going to start with the initial state Q naught, and here we are going to read the value So here A we are going to read. So here what we have to do after reading, we need to change the value, then only we can say that this already read. So here A is equal to X. We can replace it with the X. So that will be represented as A. So whenever the input A is there and X is the replacement value, and what we have to do, we need to move to the right direction. So we need to move to the right direction. So and it is reaching the one more state Q1. So here, and we need to check for the another B. So why? Because we need how many A's are there, we need to find for the next B. So initially we need to satisfy the linear bond automata, we need to satisfy for this kind of first initial value also. So after reading A, we need to search for the B and it is followed by C. So for the searching of B, how many A's in between the path, we need to skip those values. So skipping, how we need to skip that one? So here A is there. So next right direction, we have the input value A is there and one more A is there. How many A's are there? We need to move to the right direction. That is going to be replaced. So A is going to be replaced and with the A, and we need to move to the right direction. And here also, how many in next A? So here also we have A input symbol. So we have written loop statement so that how many A's are there, we need to move to the right direction into the right direction. So whenever we saw the B, so B is going to be replaced with Y. So B is going to be replaced with Y, and we are going to move to the direction, right direction, and we're going to the right direction. So in the right direction we have B. And what is the next step? In the first language, first string, we have A, B and C. So we need to search for the C. So searching for the next C. So here how many B's are there? We need to replace it with a B and move to the right direction. And we need to, so this is also finished, and we need to move to the right direction, and we saw the input value. So we will write it as a C input value, and here this C is replaced with Z, and we need to, if you continuously go the next state, so you will find the next end of the input tape. So what we have to do, again we need to go for the starting. So how to go to the first step, in the sense we need to change the direction into the left hand side. So, and this state is Q3. So here, how many states are there? We need to move to the left direction. And here, when we observe the B, so here, what is the next step? And again, we already finished A, B, C. And we need to go for the next A. So we need to replace this X, so that how we need to go for in the left direction. So left direction, how many values are there? We need to replace the same values and we need to move to the first A. So here what is that step indicates? So here left hand side we saw the B value. So B is replaced with the B only, and we need to move to the left direction. And here this already B, how many B's are there? We are going to be replaced with B only and moving to the left direction. And here when we saw the Y value, so Y is there here. So Y also replaced with Y and we need to the move to the left direction. And we saw the A value. So A is there, and here A also replaced with A and move to the left direction. And here when we saw X value, so finally the leftmost derivation, leftly we have the X value. So X value is there, we need to go for the starting again. So X is replaced with X and move to the right direction. Then we saw the A value. So then we saw the A value, and what is the next step when we go to the starting state? So X, when we saw the A value, we need to replace it with X, and move to the right direction. So then we saw, so this one is, so let me write. So first is X is there. So this already all we have written, and we just are there in this state. So here A is replaced with X and moving to the right direction. So we saw the A value, then A is replaced with A only, and go to the next state. And here we have the Y value. So after finishing this step, we saw the AY value. So here Y, when what we have to do, we need to replace the b value. Then we can't change the value of y. So y is replaced with y and moving to the right direction. So then we saw the b value. So b is replaced with, so from this state when we saw the b value, so y is going to be replaced and we need to move to the right direction. And then we saw the b value, so B is going to be replaced with B and move to the right direction. And then we saw the Z value here. So when we saw the Z, we need to go search for the C. So Z is going to be replaced with Z and move to the right direction. And here we saw the C value. So C, from here, C is replaced with Z and we need to move to the left direction. So like this steps is repeated here. So here, after completing this one, finally we are done with all the values like this. So x is going to be replaced, and y is going to be replaced, and z is going to be replaced. So from this step we will discuss. So after C, so we all change the values of all the input symbols. So finally here we are in this stage. So C is replaced with Z and move to the left direction. So here I am here, a Z is there. So here also I need to replace the Z with Z and move to the left direction. So Z is there, and here Z, after this step is going to be repeated. How many Z's are there? We need to replace Z only and move to the left direction. Then we saw the Y value. So Y is going to be replaced with Y. And how many Y's are there? We need to replace it with Y only. And here when we saw X here, so here X is there. X is going to be replaced with X, and we are going to the value. So X is going to be replaced with X, and so here in this step, so x is going to be replaced with x and move to the right direction. And here we have, so here in this step, we saw that from this state, x is replaced with x and or. So here from this state, we don't have the y input value. So when we have the y input value, we need to replace it with y and move to the right direction. So move to the right direction, that is a Q4. So here we are there, and here after this how many y's are there? So this is for one y, and here were two more y's are there. So for two more y's, y is going to be replaced with y. I am going to be changed in the move in the right direction. And here we have, after this one we have the z value. So from this state, we have the z. So z is going, finally we need to reach this one, then only the string is going to be accepted by the finite automata, sorry, a linear bound automata. So z is there, and z is going to be replaced with z and move to the right direction. And then we reach the final state, sorry. So z is going to be replaced with z, and it is going to be with z only and move to the right direction. And this is for one z, and here two more z's are there. For this step, two more z is going to be replaced, and z is or and moving to the right direction. And this is a q5, and here we saw the value this right end marker. So when we saw the right end marker, we need to replace it with the right end and move to the left, and we need to end the state here. That is q final state we need to reach. So this is about the construction of linear bound automata. So for this kind of languages, we can construct the linear bound automata. So these are the references. So here, so these are the main examples. In this one, we have discussed about the a power n, b power n, and c power n. So in this one, we need to check for the number of a's and number of b's and number of c's. So n number of a's followed by n number of b's and n number of c's, we can construct a linear bound automata. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.